never see it again. Why am I taking these pictures? All right, your midterm is now uploaded onto Canvas. So I talked about this. I posted an announcement, and I'm allowing for you guys to do a midterm analysis. This is due actually December 11th. I may have put a different date here than I put in the announcement. I would like for you guys to turn this in the week before finals. I'd like to have at least a chance to grade it. So that's due Thursday before finals, so that Friday before finals I can grade it, if not sooner than that, and give you feedback on this before you actually go into the final exam. Because it sucks to like try and revise your work and master something and not actually master it before you go in and take a final. But I will accept it all the way until December 15th at 5:50. December 15th is our final exam day. So you can turn it in right before you walk into the final. You cannot submit it for points after that. There's no benefit to it. And this is a beneficial assignment. This is not something I'm requiring you to do. Usually about half of the students in the semester do it. And if I can advise anybody, and I'm talking to everybody online too right now, those of you that do worse on the exam, have a lower grade, this assignment is for you. This is our grade breakdown. I color coordinate this. Blue is A, green is B, C is yellow, D is orange, red is failing. White is getting above 100%. So you can see a lot of our class got A's. That's what, like about a third or more of our class had A's on this exam. And then the second largest portion was getting C's. Well, a lot of the people that got C's got bumped up into B's by getting the bonus questions. Most of the people that had B's got bumped up into getting A's, and a lot of the people that had A's got over 100% with the bonus points. So those of you that already earned bonus points and got the score you wanted, this exam analysis is not for you. You're welcome to turn it in, but you're not going to benefit from it. You're sitting pretty in the class right now. It's these people that this is for. This is going to change your letter grade on the midterm. So take advantage of it. But I will say this, I do not just give out points. I think you guys know that at this point. I don't just give credit for turning something in. So here's what I want from you. I want you to provide and explain the correct answer. You have the key for the midterm, so you don't have to guess at what the right answer is. But giving me the answer is not the same as explaining it. So you can explain why your answer is wrong, or explain why the correct answer is right, or ideally do both. Say, I chose this, but that's not correct because of X, Y, and Z. And this is why the correct answer is correct. Then I want you to tell me why it's on the exam. There's a few different ways you could do that. You could go back to the learning objectives sheet that I've handed out or that I've posted online. For each of our modules, each of our sections, our units, and you could look at the question that you got wrong on the exam and you could say, well, this was trying to assess us on the learning objective in section 1, learning objective 3. I'll give you guys a more specific example of that. And then lastly, a reflection. Why did you not get it right? And listen, I get a lot of people on this that just give me the same thing. Like literally copy paste for half of their answers. And I think you can already kind of guess what it is. They give me something like, in this reflection, they say, I just didn't study enough. I just got confused. I just guessed. Okay, I mean, I get it. I feel like you're skimping a little bit, but maybe that is all it is. You just guessed, and that's all there is to it. What I don't want to see, I don't want to see you guys be critical of yourselves. I don't want you to be harsh. I don't want you to say things like, I just don't get it. I'll never get it. I'm not good at this. This isn't my strong suit. Be honest, but don't be mean. Okay? So every question should have an explanation of the correct answer, a connection to why this was even asked on your exam, and a reflection of why you didn't get this answer right. I would prefer that those all be connected per question. So formatting, there's a few different ways to do this. I think maybe I should try to update the formatting description on here. I say format. I've seen people do this a lot of different ways. I would recommend you take a picture of each problem and you just upload that into a Word document, and underneath that problem, 1, here's an explanation of the correct answer. 2, here's why this was on the test. 3, here's why I didn't get this right. And then a picture of the next problem you got wrong in a Word document. 1, 2, 3. Next picture of it in the Word document. 1, 2, 3. Some of you are very handy with your tablets, and so you would rather type or handwrite this, rather than type it up. And so I'm happy to see that too. But then again, I think pictures that go into your handwritten notes. What's really challenging is when I get people that just take pictures of the exam and upload those all at once, and then in a completely separate document, or like totally underneath it, they have all the explanations. So then I kind of have to jump up to see what you got wrong and why you're giving that kind of explanation, and it's a lot of scrolling for me. So to make this as painless for me, it's helpful if you just take a little bit of extra time to just take individual problems and answer them directly. Does that make sense? Here's what I'm talking about when I say explain why this was on the exam. If you go back to the modules and you go to any of our units, you'll find our learning objectives document. And from here you can say, well, this is on the exam because in section 6, learning objective 1B, we said we were going to learn about reduction reactions. That's as easy as it needs to be. That's all you could say, or you could just say, in class we spent a lot of time talking about resonance, so of course resonance was going to be on the midterm. Or it's important to know why compounds have different acidity levels, and that's why we're talking about acid on the midterm. I would appreciate if it doesn't say, why was this on the exam? We covered it in class. Yes, that's true. Why are we covering it in class, and why was it on the exam? I do give partial credit, but like I said again, I do not just hand out points. So you've got to have it with the 3 parts, or you're not going to get it. Yeah? Can I clarify anything on the exam analysis assignment? How many points back do you get? Up to half of your points lost. That's why it's best for those of us that did worse on the exam. You have the opportunity to earn the most points back. I think our low score was a 33%, or 33 points. So out of 70, that leaves 37 points lost. So something like 18 and a half points back. They can get 18 and a half points back, which is like 20% back towards their exam. Could shoot you 2 letter grades or more.
Is how many you lost, including the
Bonus points aren't lost. So you can't earn bonus points back. Just the graded problems. You're welcome to do the analysis on the bonus points, but I will probably skip them, and you don't get points back for answering the bonus questions. Thanks for clarifying that.
And the original blue one is the original grade before the bonus points?
That's right.
Okay.
Yep.
Sorry.
I grade in blue for the psychology of it. Psychology shows that grading in red is internalized negatively, but grading in blue is not internalized negatively. So I flip it on its head. I give you bonus points in red, but your grade is in blue. Yeah. What else? Oh, there is a problem I want to look at with you guys. I thought of this one day in my office, just thinking about it. I was shocked by the answers I got. Some of them, I think maybe they just weren't read correctly. This was the other thing. I gave you 10 points of extra credit on the exam. I meant to give you 10%, which is 7 points extra credit. I gave you 10 points, which is way more than 10% extra credit. That was not intentional, and I'm incredibly upset at myself. Like I said, I do not hand out points. I even told you guys I've thought about taking bonus points off of my exams, so I limit it to 10%.
So the extra credit questions are fun.
I think they're fun too, thank you. I loved this question though, and I got some wild answers for it. What is the smallest cyclic chiral compound you can draw? I think arguably there is a correct answer to this, but I was willing to accept many right answers. But then I gave partial credit for answers that were further and further from the right thing. So one person gave me a 5-membered ring that had like an alkene and then something else. Is that the smallest cyclic compound you can draw? No, we could go smaller and get a 4-membered ring, and then even an alkene or 2 groups coming off of it, those would be cyclic, chiral. But really, a 3-membered ring is the smallest that you can get, and you can't have an alkene here and a substituent coming off of the other one to make it chiral anymore. You'd need at least 2 substituents that are different from each other. Or you could do an alkene that is substituted and then have another substituent. Now that's chiral. And actually, one of the answers that I was hoping to see was a 3-membered epoxide, because that actually cuts down on the number of atoms by taking out a CH2 group and replacing it with one O. And then having something like a bromine at one of those positions, right? That makes it chiral, and it gives you as small of a number of atoms as possible. This was an incredibly open-ended question, but it was interesting, right? Like the challenge of coming up with as small of a thing as possible and making it chiral. So I think that if you went with a 3-membered ring and any 2 groups, I gave you 1 point. But if those groups were like more than just 1 carbon long, then you lost 1/4 of a point. You got like 3/4 of a point. But this is what surprised me. I got a lot of compounds that were not cyclic. Got a lot of linear compounds. That's what I think was just a misunderstanding of it. Then I actually liked this. I had a separate question that was just naming the functional groups, and that allowed me to actually give bonus points to a lot of people, regardless of whether it was a cyclic or chiral compound. Although some of you got away with it, and you just put alkane groups in the molecule, and all you had to say was alkane. Technically, you're not wrong. So, all right. Any other questions from the exam that you guys want to talk about together? Number 18. So we have, you said 18, right? We have staggered and eclipsed conformations. So we can automatically rule that staggered will be the lowest two energies, eclipsed will be the highest two energies. So that means 1 and 3 should be on the lowest side. 2 and 4 should be on the higher side. Was this helpful, by the way, this little diagram here? Okay, because this is not what I'm trying to test you on, is interpreting those greater than or equal than signs. And so I tried to set this up so that it was very clear. So A and B, that's 1 and 3 on the low side. I can rule out C and D right away. So the only difference is looking at 2 and 4 and deciding which of them is the highest energy. So 2 has eclipsed steric strain with the OH and the alcohol and the carboxylic acid, and steric strain with the amine and the methyl. 4 has eclipsed steric strain with the methyl and the carboxylic acid, and those hydrogens do not add to the steric strain significantly. So 2 steric strains, 1 steric strain, 2 is the highest energy conformer here. Does that help answer your question?
Well, I think the CH3 is on the larger side than OH. 2 is given that one.
I think you can make that argument that OH and CH3 might not make the same amount of strain, and that CH3 causes more strain, but not twice as much strain. This has 2 steric strain positions, 2 sets of groups that are causing steric strain. So even if this is slightly larger than this is not larger than both of these. Do you see my point there? And to that point, the methyl is causing the steric strain in both of them, plus the alcohol causes steric strain here. In class, what did we cover? Count the number of steric strains that you see, and those number of steric strains gets you there. You could also have used the fact that A and B both agree that 1 is lower energy than 3. 1 has a steric strain here and a steric strain there, 2 steric strains. B has 1, 2, 3 steric strains. Once again, we're just counting the amount of steric strain caused by those groups being next to each other. Gauche. All right. Thank you. What other questions? Natalie.
For the third bonus question, was that one, like it was chiral, but was it like meso? Like, is there a plane of symmetry on that? So was it
There is a plane of symmetry. So if you draw this out, you get something like this. I gave you a quarter of a point if you drew the compound, half a point if you drew the chirality correctly, and then like full points if you drew it correctly and discussed the chirality correctly. But this goes into a new conformation. Where we can actually see the plane of symmetry.
And it's not active because it's like the
Right.
Okay.
So optically inactive meso.
Their modules are only meso when the functional groups are either facing towards you or away, not if they're. I think I had 2 wrongs make a right on that one where I was like, oh, it's meso, but the compound that I drew wasn't.
Yeah.
So it's like it's only if the functional groups are, because like I draw the S group, right, and so I had bromine coming towards us in that first one.
Yeah.
Exactly, just like that. Yeah.
If they're symmetric, if there's a plane of symmetry, then the molecule is optically inactive.
Right.
Here, there's actually not a plane of symmetry. It's kind of like the groups are doing this, yeah, rather than the groups doing this. No plane of symmetry like this, no plane of symmetry like this. So we were looking for meso optically active. There a bonus question on this page number 4. I think one person may have gotten all 1.5 bonus points here, and that's it. It was half a point for each of the 3 missing peaks. I gave you a quarter of a point if you had like the bond type or the range correct, but not both, because you were on to something, but you didn't really nail it. But half a point for the bond type and the peak correct. So that's the sp3ch, the NH bending down in like the 1600 region, and the CO double bond in like the 1700 region. 3 peaks missing. And I got some weird ones. I had someone gave me the CO of the amide. Someone gave me CH of an aldehyde. So here's another reason I like the bonus points. Because they're usually more like short answer, I get to actually see what you guys understand. Better than multiple choice tells me. I get to see some of your thought process. So I just want to encourage you guys to keep reviewing your functional groups. Keep reviewing that correlation table. Stay up to date on it, because we'll use spectroscopy as a way of proving organic reactions going forward. This is true in lab as well. You guys are going to run a reaction. How do you know you got what you wanted? Take its spectral information. Prove that the bonds are absent that you wanted to remove and that the bonds are present that you wanted to create. Prove that the NMR spectrum has the integration and splitting patterns that you were looking for. One of the reasons I teach spectroscopy leading into the second half of the semester is so that we can have data to support our reactions. You guys notice that spectroscopy was section 12 and 13, and now we're back to section 6? That's because most textbooks teach spectroscopy after reactions with aromatic rings. And we don't cover reactions in aromatic rings in OChem 1, we cover that in OChem 2. If it were up to me, if I were writing a textbook, I would put spectroscopy right where I did. After we learn about regio and stereochemistry, we'd talk about spectroscopy as another analysis of organic compounds, and we'd use it, as we're going to all semester, as a proof for how these chemical reactions proceed. Other questions? Great. You get to hold on to these. I don't want them back. They don't do me any good. But they do you guys a lot of good. All right. We are moving through section 6. Yesterday, last class, we were working on these reactions, and we described a lot of terminology for our reactions. We said that reactions have different classifications: substitution, elimination, addition. This is something you'll see on your unit test. This is something you'll see on your final. They have other descriptions as well: oxidation, reduction. And we actually can see examples of addition that are reductive, addition that are oxidative, elimination that are reductive, elimination that are oxidative. So those descriptive terms, oxidation and reduction, are not specific to any of those 3 major classes. I think before I get into the solvents, I actually want to talk about some Regio and stereo terminology. I'm just going to introduce the names of some dead guys so that when we talk about those names later, we've already just got an introduction to it. In addition reactions that provide an H, that is at least one of the groups, typically only one of the groups, added is a hydrogen. A chemist named Markovnikov brilliantly discovered that the hydrogen would always add to the carbon with more hydrogen. So this rule is named after Markov, but that was sarcastic, by the way. I'm going to tear down his theory in a little bit. Markovnikov's rule is that H adds to the carbon with more H. What's another way of saying the carbon with more H? Not the more saturated, but close. Actually, not more either. Saturated is about how many atoms it's bonded to. But a carbon that has more hydrogens versus a carbon that has less hydrogens, I guess some context here would be a carbon that has more bonds to carbon. The carbon with more hydrogen is the less substituted. For example, in this reaction, the carbon up top is less substituted, it has more hydrogen, and the carbon in the middle is more substituted, it has less hydrogen. So Markovnikov's rule says hydrogen adds to the carbon with more hydrogen. Hydrogen adds to the carbon with less hydrogen. This usually invokes in a chemistry student the idea that hydrogen is drawn to where hydrogen already is. A hydrogen will go to where there are more hydrogens. Join the flock. It has nothing to do with that. Hydrogen is not controlling where it's going. It has nothing to do with the hydrogen. But that's the rule. Anytime hydrogen does not add in that direction, we call it anti-Markovnikov. By the way, we can abbreviate this as Mark and anti-Mark, or Markovnikov and anti-Markovnikov. So the definition of anti-Markovnikov is H adds to the more substituted carbon. Think about 10 seconds and think about this reaction. Is it a Markovnikov addition or is it an anti-Markovnikov addition? Anti-Markovnikov. The hydrogen adds to the tertiary carbon, the more substituted. So this problem, this reaction, is an anti-Markovnikov hydration reaction. Markovnikov did, I don't know, but he worked with reactions that proceeded in a specific way in which the most stable intermediate formed when the hydrogen was on the more substituted carbon. It had nothing to do with the hydrogen, though. And it had everything to do with the charge of the intermediate. So I hate Markovnikov's rule because it steals your attention from looking for charge stabilization. And that's all Markovnikov's rule is trying to get at. Both of these, it's all about charge stabilization. So we'll talk about that when we get into the reactions. We'll talk about how can I stabilize the charge during this reaction. You guys okay with that? I have to tell you it's called Markovnikov and anti-Markovnikov, but I'm going to explain why it happens. All right. Let's talk about this addition for a second, to the right. Can I use Markovnikov to describe this? Is there a hydrogen added? No. So I can't use Markovnikov to describe the Regio chemistry. How about this addition reaction? Can I use Markovnikov to describe this? Actually, not really, for two reasons. There is no carbon more substituted, and there is no carbon less substituted. Markovnikov's rule only applies if the two carbons of the alkene or the alkyne have different degrees of substitution. But these carbons are equally substituted. So Markovnikov's rule doesn't apply at all. And hydrogen adds to both carbons. So Markovnikov's rule still doesn't apply. If it's both Markovnikov and anti-Markovnikov, it's not Markovnikov at all. Okay. Do you guys agree that this describes regiochemistry? It describes where in the molecule groups will be added, more substituted or less substituted carbons. In terms of elimination reactions, a man named Zaitsev found that the more substituted alkene prefers to form. We'll talk more about alkene substitution, but it really just means from the two carbons of the alkene, how many carbon groups are coming off of it. An alkene with more carbon groups attached, more substituted. An alkene with more hydrogens attached, less substituted. But now I have to consider two carbons. Of course, if a less substituted alkene forms, we call it anti-Zaitsev. But another man also took credit for this. And so instead of calling it anti-Zaitsev, this is sometimes called Hofmann elimination. You'll see both. I often call it anti-Zaitsev just to stay on one page, but Hofmann elimination is equally accepted. And
Sorry, did you say that if it's bonded to more carbons, it's more substituted?
just like it is with, primary, secondary, tertiary, quaternary, more carbons, more substituted. But now you have to consider both carbons of the alkene to say that the alkene is more substituted. You're welcome. I didn't give a lot of elimination reactions on here. I've only got one. Can I describe this reaction as Zaitsev or anti-Zaitsev? Which one? I would disagree. You want to try again?
Is that a tertiary carbon? Oh. Yeah.
Yeah, so let's say it's this carbon and this carbon that form the alkene, as opposed to this carbon and this carbon, or this carbon and this carbon. I would disagree, not that it's anti-Zaitsev. I would disagree that you can use regiochemistry to describe it. This is neither Zaitsev nor anti-Zaitsev. There's only one possibility for the alkene. So I should give you an example of an elimination that can be Zaitsev or anti-Zaitsev. Anti-Zaitsev, less carbons coming off of the alkene. Zaitsev, twice as many carbons coming off of the alkene. Does this describe regiochemistry? It says elimination, where the alkene forms, will either be in this direction on the molecule, towards this substitution of carbon, or it'll be in this direction on the molecule, towards this substitution of carbon. That is regiochemistry. Where will the chemistry happen? These are regiochemistry terms. You guys okay with that? It's clear, right? Do you know, I was talking with a colleague recently, and I wish I had introduced Unit 2 completely differently. Unit 2, which was functional groups, alkane nomenclature, all nomenclature, conformers, chirality. Unit 2 is all regio and stereochemistry. What is functional groups? What are functional groups if not specific descriptions of regiochemistry? If this atom is bonded to this atom and then in this pattern, that's this functional group. You're looking at a region of atoms, that's a functional group. That's regiochemistry. And all of our conformations and our stereochemistry and chirality, that's all stereochemistry. So we are really just expanding off of that as we move here. All right, some stereo terms. We have syn addition. I'm just going to give this example here with a generic halogen X. But it says when two groups add, they add with the same stereochemistry. Notice that it's not called cis addition, although we say that those two groups on the same face are cis to each other. We call it syn addition. They add to the same face. And here's one of the reasons. If I took a different alkene, one that is not in a zigzag conformation, but one that is in a zig-zig conformation, the product I get is a stereoisomer, where one X is wedged and one X is dashed. And yet this reaction is still a syn addition reaction. Why? Because this is not the conformer that the product forms in. This is just the more stable conformer. Instead, the conformer that forms is syn. The two groups add on the same face. And then it just relaxes into a lower energy conformation, which is what we see. To clarify, syn addition does not describe the stereochemistry of the molecule you look at necessarily. Syn addition describes the stereochemistry of the product as it forms. And oh my God, I just realized this is an anti-addition reaction. Total brain fart. None of you know that, and that's great for you, but this is really bad for me. Okay, we can make a quick change. I'm so sorry. We gotta erase sin and write anti. And we gotta change the stereochemistry we're looking at here, so that in our first reaction, it's actually wedge and dash. And in our second reaction, it's actually wedge and wedge with a wedge and dash conformer leading up to it. So change this stereochemistry, change this stereochemistry, change this stereochemistry. Wow. I wish you knew how embarrassing that feels for me. That's terrible. 9 semesters straight I've been teaching OChem 1. Summers included. What the heck?
Wait, have you always taught it and you just now realized? Or is this?
No, I just,
Oh, okay.
like, huge brain fart. Huge. I wanted to do sin, but I put an anti-addition reaction. All right. Is that confusing enough for you guys? The fact that anti-addition doesn't necessarily describe all conformers, just the conformer of the product as it forms. It describes how the groups add relative to the initial conformation. But we can rotate things as much as we want. Okay, then the other is sin addition. And the example I'm going to give here has a ring and osmate. That is OS04, not O504. That would be a terrible compound. OS04, osmate, or osmium tetroxide. And my two groups here are either wedged both or dashed both. Is that compound I drew chiral, achiral, or meso? You want to prove it? Anybody else want to support that? Meso? I not second it, support it.
Oh, support it?
Yeah.
The plane of symmetry is between the two OHs.
Good.
You say, yeah, thank you.
So it has 2 chiral centers, and those 2 chiral centers are symmetric to each other. So 2 chiral centers and a plane of symmetry, meso. Good.
What did you say the chemical you were adding was?
Osmium tetroxide, OS04.
Okay, that's an S, got it.
Yeah. How could I? Is that a cursive S? Looks like an ampersand. Could do the Superman S on there. I'm not good at the Superman S. Okay, I talked here about how conformations can make it look like it's not sin or it's not anti. And you have to rotate it into the conformation that proves that it is. Is there any conformation of this ring that makes it look like those 2 groups are not sin? Can I ever get a conformation like I did here, where it looks like they are anti to each other? Why not? This one's a ring. And those rings are locked. Remember, with rings, we introduced cis and trans stereoisomers. I can have cis 1,2-dimethyl cyclohexane. I can have trans 1,2-dimethyl cyclohexane. But I can't have cis 2,3-dibromobutane and trans 2,3-dibromobutane because a linear chain can rotate so that those groups appear cis and appear trans. But the ring is locked. If it looks cis, it's stuck cis. So here, syn and cis work hand in hand. Trans and anti work hand in hand. But on linear chains, cis and syn mean different things. Anti and trans mean different things. Anti is telling you the groups added through a chemical reaction in a specific way. Trans is only relative to rings when they're stuck in that conformation. That's why we're using different terms. We're not calling it trans addition and cis addition. We're calling it anti and syn addition. All right, any questions? Stereo terminology for those two or regio terminology? Stereo terminology. They describe the stereochemistry of the products. Debate. A reaction easily could have both regio-specific terminology and stereo-specific terminology. Or a reaction can either be described by regio-specific things or described by stereo-specific things.
First one. Can we describe by color?
Why not? It can be described by where the groups are going to add and with what relation those two groups are going to add to each other. But some reactions are referred to as stereo-random. They're regio-specific. They'll always, react in this way, but their stereochemistry is not predictable. Others don't really have any regio-specific terminology, but they're definitely stereo-specific. And then some are both regio-specific and stereo-specific. So we're going to learn a lot of reactions in this unit. And those reactions, we'll go through each of them and say, this is their regiochemistry, this is their stereochemistry. And we'll see that reactions have all different kinds of combinations of those. All right. Unfortunately, I didn't oh my God. I made a typo on that Lindler's Catalyst one too. I give up. This worksheet did not come out the way it needed to be. You guys remember there was a mistake up here too? I missed a carbon on this group. I don't know if it's worth fixing, but this alkene is supposed to look different. Because that reaction, that's not even the alkene. That reaction is what we call a syn addition reaction, and so the alkene that's made is very specific. And I drew it trans. You'd think it's my first day on the job, seriously. All right, let's talk about something I can't possibly screw up. Solvents. Just watch. These are our three general types of solvents, although there is another way we could classify these. We could say that there are organic solvents that fit all three of these descriptions, and aqueous solvents. Aqueous solvents only ever fit in this polar pronic category. Nonpolar solvents are those that don't have any permanent dipoles, no carbonyls, no heteroatoms for the most part. Some of the most common non-polar solvents are hexanes. It's actually very interesting, the fact that this is plural. If you are to order hexane from a chemical distributor, it will be much more expensive than purchasing hexanes. Hexanes here are a mixture of structural isomers that all have chemical formula C6H14. So that includes N-hexane and also methyl substituted pentanes, and then maybe also a couple of butanes, dimethyl substituted butanes, but I think less so. Why are these considered hexanes if they don't all have a six-membered parent chain? They all have the same chemical formula, and their boiling points are relatively close to each other, so they're hard to separate, which is why if you buy hexane, just N-hexane, it's much more expensive because it's harder to make it just pure N-hexane. The only other nonpolar solvent that is commonly used is tetrachloromethane. Or methane tetrabromide. That's not bromo. Oh. I said bromo. Okay, I wrote chloro. God damn. Okay. Tetrachloromethane. Nonpolar, despite having 4 heteroatoms. There is no region that is more polar or less polar in this compound. Tetrachloromethane is incredibly toxic. Its bottle, we have some in the chemistry lab downstairs. Its bottle has a big skull and crossbones on it, literally. So it's advised not to work with it. Oh, you guys that did the essential oils lab, you would have actually seen this as a last resort. If you can't possibly get any of your essential oil to the IR, you could dissolve some of it in this and then put it on the instrument to try and get the IR from it. Because it only absorbs in the carbon halogen bond range down in the fingerprint, so it's not going to mess up anything in your absorption. All right, what does aprotic and protic mean? When we say polar aprotic, polar protic, what are we describing? Protic is it does have something to do with proton, just one proton. What is a proton? A proton. What is it? Not hydrogen. Hydrogen is a proton and an electron, or 2 protons bonded by 2 electrons, depending on if you see atomic hydrogen or elemental hydrogen. But you're on the right track. A proton is hydrogen ion. The hydrogen ion, H plus, is a proton. So compounds that have a proton to give, or in other words, acidic compounds, even if they're slightly acidic, if they're even slightly capable of giving H+, then we call them protic solvents. Okay, to be clear, not every compound that has a hydrogen is protic. It has to be something that's willing to give that hydrogen away. So here are some of our most common polar aprotic solvents. DMSO, that is dimethyl sulfoxide. Anybody ever worked with DMSO in a biology lab? Yeah, one of you. The rest of you will someday. Very common organic solvent. I have a former student who said they had taken DMSO as like a way of ingesting a drug, getting a drug into their body. I didn't know you could do that, but they say you can. THF. Tetrahydrofuran. Furan is the 5-membered ring with the ether that also has 2 alkenes. Add 4 hydrogens to that, and you have tetrahydrofuran. That's an ether compound. Another common one is diethyl ether. Also written as ET2O. What does ET abbreviate there? Not ether. Good guess. Extraterrestrial. Bad guess.
I can't make a joke.
No, it was a great joke.
I mean, I could go home.
I didn't tell you to come. Now you have to stay. ET is short for ethyl, diethyl, ET2O. This is one that you guys use in the organic lab quite a bit. We have ethyl acetate. What functional group do you see in ethyl acetate? Ethyl is not a functional group, but thank you for contributing. Acetate is technically not a functional group, but a compound. An ester, correct. There is an ester in ethyl acetate, but there is no protic group. None of those hydrogens are attached to an acidic atom, right? They're all attached to carbons. That's pretty much all. I think actually there is another way that you'll see ethyl acetate written, and that is as ETOAC. Ethyl ET. Acetate is written as OAC. I think the last one I want to give you here is acetonitrile. CH3CN. What functional group do you see there? What? Methyl's not really a functional group. A nitrile group, which is also called a cyano group. Okay, there was one more I wanted to give you. I'm really running out of space. I want you guys to see it. That's DMF. That's dimethylformamide. Formamide is an interesting word. It tells you both that there is an amide functional group and an aldehyde. Form is a suffix, or a root that tells you a 1-carbon aldehyde. Who's heard of formic acid? Formic acid is a 1-carbon aldehyde that is also a carboxylic acid. Formamide. Who's heard of formaldehyde? Made a really dark joke once about formaldehyde my first semester TAing in grad school. I was like, yeah, formaldehyde, what we'll all be stuffed with one day. Yeah, that's more laughs than I got out of them at
I just used that today.
8 a.m. on a Thursday, so that could have been hard. Formamide, formic acid, formaldehyde. The form is telling you that there is a 1-carbon aldehyde functional group. All right, none of those are protic. Here are the protic the polar protic solvents. Water. That OH from water can be donated as an acid. This is the one and only aqueous solvent. All of these other ones are organic. I'm going to put ROH, alcohols. But if you want some examples, we can work with methanol, ethanol, isopropanol. And we can write them different ways. I've given some abbreviations. MEOH, ETOH. What does the IPROH tell us? Isopropyl. The I stands for the iso in isopropyl. And then the last one here is acetic acid. Often written as ACOH. Remember ETOAC? Now I've got ACO bonded to the H instead. So that ester that we had before, we've got the same carbon chain with the carbonyl, but I'm swapping out an ethyl for a hydrogen. Here's another thing I want you to notice. The AC and the O, they can swap positions. AC is standing for acid, acetate or acetic, but the O is actually written as a connecting group. So it can be OAC and it can be ACO. Once again, we're not going to see solvent written in every reaction, but when it is necessary, it's going to be written. And we'll talk about how some of these solvents actually run reactions themselves. We call those reactions with solvents is called solvolysis. All right, why don't we take a 5-minute break so you guys can get up and move around. And when we come in, we're going to look at some other aspects of organic reactions. Everybody got this down, right?
Go back more. Not the worst problem.
It's like, okay, we have to exercise the lab now.
The AC stands
That's
for
so iconic. It's so sad, but it's so iconic.
because on the bottom. This is called common names, not systematic. Oh, if you were to name
It's kind of working right now.
different animals, you would call it ethanoate. Acetic acid is ethanoic acid. Oh, ethyl ethanoate, a two-carbon chain, and a two-carbon acid. Ethyl ethanoate. Acetic acid is ethanoic acid. Two carbons, carboxylic acid.
Not
Acetonitrile is called ethane nitrile.
yeah.
Ethane nitrile. Two carbons.
Well, I was ignoring 6.
Oh. That's a systematic name. Aceto, acetate, acetic. Those have all come around to represent a methyl group and a carbonyl carbon. Carbonyl carbon is usually CO double bond. And the nitrile is not a CO double bond. And yet in O2, you'll find that most of the carbonyl groups, when you learn about aldehydes, ketones, esters, acids, amides, and hydroxyl, they also include nitriles. They share similar chemistry. Yeah, they've got a pi bond that can allow them to do addition reactions, and they've got partial positive on the carbon, so they're electrophiles. But I am with you. I don't like common names. I was talking about the form is also a common name. Formaldehyde, formic acid, formamide. But you could use systematic naming as well. You could call it dimethyl methanol. Instead of formic acid, you could call it methanoic acid. Instead of formaldehyde, you could call it methanol. Thank you. Good question. Do you guys know how the form root came to be? The form of formamide, formic acid, and formaldehyde? It comes from the Greek. Formic acid was the first time it was used to say the acid that is produced when an ant is killed. If you kill ants, some of them will release this acidic compound, and it's formic acid, the ant's acid. Not to be confused with antacid, which is not a pun there. So form is Greek for ant. Not cool. It's not systematic at all. It has nothing to do with systematic nomenclature.
Also, they found this out by killing ants.
No, they just said, oh, when you kill an ant, there's this acidic compound that comes out. Here's this acid made from the ant, formic acid. But then when they discovered what the compound was, then they just applied it in nomenclature throughout. Formaldehyde, formamide. And then you see something similar happening with the acetate. You've got the acetic, acetate, acetonitrile, which is meant to indicate a 2-carbon carbonyl. A CH3 carbonyl, CH3 carbonyl, CH3, not really a carbonyl, but actually a CH3 nitrile. And a lot of organic chemistry textbooks, they'll show you chemistry with all the carbonyl groups and with nitriles. Nitriles have similar enough reactivity to the other carbonyls that they kind of group the nitrile in with the larger group of carbonyls. So acetonitrile. Do you guys know any other compound that has this kind of acete prefix, the AC beginning? Acetone. And what do you hear in the name acetone? Ketone in the suffix -one. And that's exactly what acetone is. It's that 2-carbon carbonyl that is actually a 2-carbon carbonyl from either side. It's the 2-carbon carbonyl ketone, the acetone. I hate it here. Not here. Okay. Moving on to reaction coordinate diagrams. How many of you remember reaction coordinate diagrams from your general chemistry course? Oh. I mean, maybe it didn't quite look like this. I'm missing all the lines, the bumpy roller coaster. Okay. I really should sit in on some of your Gen Chem 2 lectures. This reaction coordinate diagram it shows the energy requirements, or the energy of the molecules as a reaction proceeds. So far, we've said, here's a molecule, here's an arrow, here's a product. But we haven't investigated, how does that change occur? What bond breaks? What bond forms? How much energy does it take to do that? Are there other things in between? So there's some terminology that I want you guys to learn. Of course, on the far left-hand side, we have our reactants. You can also call this the starting material, or SM. And on the far right side, you have the products. But in between, there are other compounds that form intermediate in the reaction. We call those intermediates. In order for bonds to break and for bonds to form, actually, I should say that wrong. I said that wrong. In order for bonds to break, energy has to go in. Although, yes, bonds forming releases energy, in order to get those two groups, those two atoms close enough to each other to form a bond, also requires some energy. So from our starting material up here to our first intermediate, we require this activation energy. And this hump that has to be overcome before getting to this next level, this is called an activation barrier. I don't need to get just from here to here. I need to go higher than that before I can fall down into this well. So up here at position 1, this is called a transition state. And transition states are often shown in brackets with this double dagger put on the top right. I'm not sure why they call it a dagger. We've got this symbol indicating transition state. This is a theoretical structure. Transition states cannot be isolated. They're too high of energy. They sit at this tippy point between two lower states. So you cannot isolate a transition state and analyze it. So instead, we theorize transition states. And one of the reasons they're theoretical, the reason they're so high energy, is because this is the moment where bonds are breaking or forming. This happens over the course of femtoseconds or picoseconds. Forget my scales. That is 10 to the negative 12 or 10 to the negative 15 seconds. These states exist for less than a fraction of a second. To show you a transition state, we show dotted lines. So I'm going to zoom in and then zoom back out. No, I can't zoom in that way. If you look on this diagram below, or on your options below, you'll notice that some of these structures have dotted lines in there. Those dotted lines are bonds that are breaking or bonds that are forming. How can you know? How can you know if you are looking at a bond that is breaking or a bond that is forming? If you are sitting here and you're looking at bonds forming and bonds breaking, how do you know what it's doing? It's not doing either. It's at a tipping point. It could fall one way, it could fall the other. Yeah? Which way is my pen going to fall? To the left or to the right? Neither. And that actually gets into a whole other point about reaction coordinate diagrams. There are three-dimensional models of diagrams that can say, you might go in this reaction in two different ways, but you might also fall down a different well. That's for another day.
No, thank you.
Transition states are bonds that are breaking and forming. You don't know what is happening. You just know that those bonds don't exist. With dotted lines. There are three transition states here. 1, 3, and 5 are all transition states. Here, at position 2, we see for the first time reactive intermediates. Reactive intermediates can be isolated, or at the very least, using a technique like our NMR downstairs, you could at least analyze it. It may be challenging to isolate it, but you could analyze it. But despite the fact that you could isolate it or you could analyze it, they continue reacting. They're not the final product. And you'll notice that reactive intermediates often sit higher than your products and your reactants, which is why they keep reacting. They're trying to get down to a lower energy state. Sometimes we refer to them as just intermediates, just to make it easier. but the fact that they continue reacting is why we call them reactive intermediates. I think throughout the semester, we're pretty much just going to call them intermediates. So here, I go through a transition state from my reactants, and I get to my first reactive intermediate. From there, I have to go through a second transition state before I drop down to my second reactive intermediate. And then in this reaction, I go through a third activation barrier, a third transition state, and I get to my final products.
With the lines.
The lines probably, probably would have been helpful. It used to have lines. I dug this out of an archive. I don't know where the lines went. So if you guys don't mind, I might erase those definitions. You guys good on the definitions? You want a minute? I'll erase those definitions so we can kind of see more the structure that's going on here. So this reaction coordinate diagram, it says first, the compounds must go through a very high energy before they come down to this reactive intermediate, then a slightly less high activation barrier before they come down to a low energy again. But they must overcome one more barrier before they get to the final products. These are each called elementary steps. I'm sorry, I feel like I can never quite word it right. I'm saying the elementary steps are separated by the transition state, but it might be better to say the elementary step is the transition through the transition state. An elementary step is going from reactants to the first reactive intermediate through a transition state. An elementary step is each time a bond is broken or a bond is formed, or whatever is needed through a transition state. How many elementary steps based on this reaction coordinate diagram? One, two, three. 3 elementary steps, 3 transition state barriers to overcome. One of these steps is called the RDS, the rate determining step. What is the rate? What is the rate at which you move down the highway? 90 miles an hour if you live in Utah. Miles per hour. The rate of a reaction is often molar per second, or something of that nature. How much product do you make in what concentration every second? What limits the production of product is that highest activation barrier. Here, as soon as my starting materials get up over that first activation barrier, they possess all the energy they need to go through the rest of the transition states very quickly. It's only once they get to the top of that transition state that, like a roller coaster, they'll quickly move to the end. That first step determines the rate of the reaction. But it doesn't need to be the first step. If we imagined that this second step was the rate determining, I would see starting material start to transition here, And as they start to build up energy, some of those molecules are actually going to go backwards. And some of them are finally going to get enough energy to finish out the reaction. So the rate determining step is what? The tallest transition state. The highest energy transition state. You guys ever been on a roller coaster like that? You get dragged up one of these hills and then sent down a little curve just to be dragged up another hill. It's kind of annoying, right? But imagine if your roller coaster dragged you up that hill and then brought you down and then dragged you up a little bit and then let go and let you slide all the way backwards and you had to start all the way back over. That's what molecules sometimes do. They run into each other, they do an elementary step, they run into each other again, and they reverse the elementary step instead of going forward. It's not until you get over the rate determining step that you'll actually quickly cascade to the product. So, together, I want you guys to work on filling in where these structures along the bottom go. So you're going to take the numbers along the reaction coordinate diagram, and you're going to correlate them to the structures that you see. Based on the starting material, find a transition state that has bonds that are currently present, that are starting to break, or that could be starting to form. I'll give you a hint. If we look at this first structure, I can see that the carbon of this tert-butyl group is bonded to an OH. Okay, my starting material, the carbon of that tert-butyl group is bonded to a chlorine. This cannot be my first transition state because I don't have a covalent bond yet between C and O. I need to get that by the end. So you'll notice that transition states look a lot like a mixture of the structure before it and the structure after it. So use that guide to piece together where these are. I'll come around and help you guys out with this too.
So wait, I did have a question just to confirm something. So the roller coaster example. So you mentioned that like you can reverse steps through that backup.
Yep.
Are the RDs, are those usually like the ones that you can't pass if you already go down that way, or is there?
Oh, no. In fact, there's something called the microscopic scale of reversibility, which says that anything that goes forward can go backwards. So
I know there's certain like biological processes where there's certain steps that are almost irreversible.
Right.
Just how
the energy strain.
What is the word? Exogenous it is? I don't
Yes.
remember the word.
Yeah, we sometimes call them energy wells.
Yeah.
The energy to form it is not very large, but the energy to reverse it is incredibly large. This happens a lot with carbon-carbon bond formation. It's very easy to form a carbon-carbon bond. It's very hard to break it.
So we're not necessarily saying that these RDs are irreversible. They're
Correct.
just harder to reverse than other things.
Not even necessarily. This molecule, for example, has an equilibrium.
Okay.
And it
I guess
does.
I gotta get out of biochemistry.
It is hard to actually push it always to the product.
Got it. Okay.
Do you want to work with it? Yeah. Elliot over there is by himself too, or Maisie back here. So feel free to join if you want to. And then you can always come back when we move on. You're calling this number one. Well, number one is a transition state. So it should have the brackets and the double dagger. I mean, the bonds forming over here.
Yeah. So that makes sense. So we know that 2 and 5 are away. That would make sense, yeah, because this one was a dash line. So that means that the left one to the left.
Oh, I see. So this is. Oh, yeah. That's okay. Yeah. But you did a good job.
That likely means left is fine. That's where it's the chlorine's ripping the hydrogen off of itself. There's two
A surprising number of them are just one step.
I was really surprised.
You know what catalysts do though? Catalysts will take a reaction that's perceived by a number of different ways. And they'll lower the activation energy, but change how many steps it takes. So sometimes you could get a one-step reaction, but it takes a ton of energy. Or you introduce a catalyst, and now it's a three-step reaction. It's like a fraction of the energy. Yeah, there are some cool ones. But they're hard to make. And I don't see a lot of good examples, so this is just kind of an introduction. And we'll use it as a way to model what is happening in the reaction. You guys feel good?
Yeah, that was
Pretty straightforward. Yeah. Great job. How do you guys feel?
Incredible.
Not quite as bad.
Good. I'm glad to hear it. Keep it up. You guys feel good? Good.
I was just saying, I'm trying to confirm if these are on here because this one matches. When I was able to look up this one. The problem is that we're looking, there's things that I don't know.
Yeah, so with your chill, girl.
Well, we start with bond at zone, right? Maybe it's not due. Yeah. Where
That one is.
I think it was the only one I knew for me.
This is the only one that matches almost exactly.
Which of these are transition states? We don't 1, 3, and 5 in the transition.
I'm gonna try to identify that. I can count.
And we represent a transition state with brackets instead of no question. If I start with bonds form, if I start with bonds form, between particles, and this is what happened after the so the balance of particles everybody feels like
It's like that, but I don't think you're
based on my intermediate,
Don't have to take.
to get healing and break the All right.
Yes.
Natalie, you got it?
Actually, I have
I'm never here.
Yeah, the ones that canceled in or the ones that were Here we see the carbon chlorine bond breaking, and then we see the carbon oxygen bond forming, and then we see the OH bond breaking.
There's this huge
Okay,
There's also this huge chunk in front of you.
a lot of things could have happened here, but based on the options given, there's only one plausible pathway. First, my possible intermediates are in the boxes, which correlates to the boxes, and my possible intermediates are in the brackets, which correlates to the brackets. So that was not meant to be a trick. The transition states and the intermediates were handed to you. If these are my possible intermediates, one where only the carbon-chlorine bond has broke, and one where a carbon-oxygen bond has formed, which of these intermediates can I get to from my starting material? Only this one. I can't both break the carbon-chlorine bond and form the carbon-oxygen bond at the same time unless I have a transition state that shows the carbon-chlorine breaking and the carbon-oxygen forming. So this must be my first intermediate formed by the carbon-chlorine bond breaking. Remember we said transition states are bonds breaking and or forming. This is a transition state with a bond breaking. After I get this carbon cation, then my oxygen can form a bond with my carbon. So I see transition state 3 is where my carbon and oxygen are beginning to form their bond. Here's a transition state with a bond forming. And then I get to 4, my intermediate, where the carbon-oxygen has formed their bond, but I don't have an alcohol, I have a protonated alcohol, and I don't have HCl, I still have the conjugate base, Cl-. So what I need to do is break an OH bond and form an HCl bond. So my last intermediate, breaking of the OH, forming of the HCl. But remember, is it breaking or forming? It's both. It's neither. It's a transition state. It's where bonds are breaking and or forming. We've got those dotted lines to say it could tip back the way it came, it could tip forward. Okay. This should feel familiar to something we looked at in Unit 1. Arrow pushing. Showing bonds breaking and showing bonds forming. So scroll down a little bit further on your page, and we get to the most coveted part of organic chemistry. Reaction mechanisms. How many of you knew mechanisms were a part of OCHEM before you came into this class? Oh, okay, this is going to shock you all. Mechanisms show the electron arrow pushing for those elementary steps. And here's the deal. You don't get to decide what the elementary steps are. Researchers have been studying it for centuries. Markovnikov, Zaitsev, Hoffman, those types of chemists are the ones that were trying to push towards explaining how reactions proceeded. So we're going to be learning a lot of reactions. I know some professors that teach all the same reactions we learn and test on any of the mechanisms. I'm going to select which of the mechanisms we're going to focus in on. Because it's my belief that if you can master the mechanisms that I choose, you could apply that knowledge to any mechanism. But there are some mechanisms out there that are just absurd. They're not intuitive, and they don't help you understand chemistry better. So the mechanisms we're going to do are just the foundation of good intuitive chemistry. And then the other mechanisms, not as intuitive, not really worth our time. However, you can look up reaction mechanisms for all of the reactions we do if it helps you explain how things are proceeding. So let's look at this reaction mechanism. Let's add arrows in. What I see here is an alkene and HBr, which goes to form some carbon cation. We'll call it a carbocation, cute little nickname. The carbocation plus a bromide ion that forms in between. We've talked about arrows like this before. Carbon-carbon bond breaks, which means I need to have an arrow that starts from the carbon-carbon bond and goes towards something else. What other bond breaks? Good. Hydrogen to bromine bond breaks. So I need to have an arrow from the HBr bond to what? HBr bond towards Br. Because bromine owns those electrons, and it's the only way I can make bromide. So I'll start with that arrow because I know it. HBr bond breaks. When the carbon-carbon bond breaks, it leaves the carbon-carbon bond and it goes to, based on the reactive intermediates that could possibly form, we know the carbon-carbon bond breaks, but what bond forms in these structures? A carbon-hydrogen bond forms. It's not explicitly shown, it's implied. That's CH, CH2. Carbon with no hydrogens, carbon with one hydrogen. So the carbon-carbon bond breaks, and it goes to the hydrogen. Does my arrow here indicate which carbon takes the electrons? It doesn't. That's why there are two possible intermediates. One intermediate where the carbon on the bottom has used the electrons, the carbon on the top has lost them, and the intermediate where the carbon on top uses and the carbon on bottom loses. Could both of these intermediates form? Potentially, but based on the product that I see, which intermediate only forms? I've got intermediate on top, intermediate on bottom, more for top, more for top. Anybody want to argue for the one on the bottom?
I say bottom because the bromine is the fourth bond on top.
Okay, so how will bromine bond to this carbon if it has an octet? So here's another spot the difference. What's the difference between these intermediates and this product? The formation of a carbon-bromine bond. That's it. No other bonds break, but a carbon-bromine bond forms. Which carbon does the bromine bond to? The tertiary carbon. Which of these intermediates allows the tertiary carbon to accept a new bond? This intermediate. So to finish the mechanism, what we would say is, this is a possible intermediate, it doesn't form. The secondary carbocation doesn't react. The tertiary carbocation accepts electrons from bromine. That's your mechanism. How many elementary steps? 1, 2. By the way, you can show these elementary steps separately as well. You could say starting material goes to product, redraw the product, starting material to intermediate, redraw the intermediate, intermediate to product. This is a fully sequential mechanism, but what I just described is also a stepwise mechanism. You draw the arrows for one, and then you draw the arrows for step two. Dang, I'm sorry. I took us way past time. Here's where we'll pick up on Monday before we move into section 7. Feel free to work on this over the weekend. I want you guys to think about what intermediate might exist in between here and what arrows you might be able to use to get to this final product. The final product, by the way, has other compounds, H3O plus and Br minus. We'll pick up talking about this, and then I have a little game for us to do at the start of Monday's class as well. And we'll move into section 7. Section 7 should be pretty quick, and then it's section 8, reactions, the rest of the semester. Have a good weekend, guys. See you Monday.